Hello, we are Team Sunrise, and our project is a solar panel battery efficiency tracking. The gist of the project is to give concise and easy information about a user's solar panel system. This includes the energy the panel produces, the energy stored in the battery, and the energy demand of the house. This is all given in an easy visualization through an app, which will show the percentage of the battery being charged and the kilowatt hour of energy produced and used.
This is the team. My name is Maddie Emsley. I'm in electrical engineering, and my project role is the load or home integration and measurement.
My name is John Chan. I'm in electrical engineering. My project role is battery integration and measurement.
I'm Alex Goebel. I'm in computer engineering, and my project role is software and interface designer.
I'm Samartha Saxena. I'm an electrical engineer, and my project role is hardware-software communication.
I'm Ray Chen. I'm in computer engineering. My project role is panel measurement and integration. And now each subsystem will have its own video demonstration with more details into it.
Hi, my name is Ray. My subsystem is solar panel measurement and integration. In the schematic, I'm planning to use the voltage sensor and the current sensor to check the output of the solar panel, and the voltage doubler to power on the current sensor. I'm still at the process of debugging the voltage doubler. The expected output of the voltage doubler should be something like this. I'll use an ADALM2000 as my power supply and signal generator. This is my voltage doubler circuit. And let's see the output of the voltage doubler. So when we apply a 5 volts peak to peak 1000 hertz sine wave signal, we should get at least 9 volts of DC. However, the circuit I built right now can now outputting a DC voltage, but it's not doubled. I'm currently sending a 5 volts as an input voltage to both current sensor and the voltage sensor. To simulate that the 5 volts solar panel input. Besides that, I also send 5 volts as a power on voltage to the voltage sensor. The red LED light represents that the voltage sensor is receiving voltage and the voltage sensor is power on. On the breadboard, since the current sensor is not power on, the yellow LED light is not light up. Then if I use a signal generator to generate a 10 volts peak to peak 1k hertz signal, as you can see, the green light represents that it is receiving the data. Now let's see the output for the voltage doubler. Although I'm still on the progress of debugging this, I'm able to generate the DC from the AC signal with no other issue. So after supplying the signal, I was able to get around 8.9 VDC, and that would be our power on voltage for the current sensor. Last, after applying both signal to power on the current sensor and the simulated input 5 volts DC, we can see that the yellow light is light up, and this indicates that it has a current flow through.
Well, this is the subsystem that has to do with the battery system integration and measurement. I've separated the subsystem into 3 parts: the battery pack, the battery management system, and the battery measurement system. So far, I've done the battery pack and the battery management system. So for the battery pack, I'll be using 18650 batteries. The organization will be in a series of 10 and a parallels of 2. This would equal to a total of 36 volts and a capacity of 144 watts. So this is the battery pack that I've organized, and I've added a battery management system on top. Each connection here corresponds to 2 batteries in series, and I know that this battery pack is working because when I check the voltage, it shows me that I'm in the range of 36 volts. And with this, I'm gonna be able to find a way to make a battery measurement system to check how the capacity, the state of health, and etc.
This is the load integration and measurement subsystem. I've designed a electric meter that has a voltage and current sensor. The current sensor requires 10 volts of input supply power, and how I've done that is I've designed a voltage rectifier or a voltage doubling circuit using a capacitor charge pump and a 555 timer integrated circuit. I'll demonstrate the voltage doubling now. .6, almost 10 volts of power. I've designed a signal generator using this circuit that produces a sinusoidal waveform. Another 555 IC timer is used. This timer produces a square waveform that oscillates between high and low in astable mode. Using an RC circuitry, I have determined the frequency to be approximately 7.2 kilohertz. With an LC resonant combo circuit at the output of a 555 timer right here with capacitor and inductor, I am modulating this waveform to produce a sinusoidal wave. This is the source signal that is applied to both the current and voltage sensors. With these red LED indicators, both of my current and voltage sensors are indicating that they are detecting a signal source at their inputs. My next steps are to translate this circuit design into a printable circuit board and to complete my MATLAB Simulink model of my hardware to produce realistic outputs at high voltage of 220 volts and 0 to 100 amps of oscillating current. Thank you.
In this part, I will go over the communication apparatus subsystem and its major components. Here we have the Raspberry Pi 3 that will handle most of the processing, a circuit board that can vary the input voltage, and an ADC chip to send digital data to the Raspberry Pi, and an analog discovery 2, which acts like a power source and oscilloscope. We also have the accompanying code for the Raspberry Pi, as well as the accompanying software for the analog discovery 2. Starting on the circuit board, a AC voltage is fed from the analog discovery 2 at these pins here. From there, a potentiometer can change that RMS voltage and feed it into the A1 input pin of the ADC chip. The Raspberry Pi 3 can feed in the VDD and ground for the ADC chip, which is at 3.3 volts. The SCL and SDA output of the ADC chip is also fed into the appropriate pins of the Raspberry Pi. Using the accompanying software for the analog discovery 2, any AC voltage waveform can be simulated. Then using the 82's oscilloscope, I can measure the input voltage at the A1 pin of the ADC chip and use that value to determine within my Raspberry Pi code the conversion between what is being read at the A1 port and what is being outputted. For a quick rundown of the code, these are the basic libraries that need to be imported, which basically allow communication between the ADC chip and the Adafruit IO cloud server we will be using. This is the instantiation of the ADC chip, and this is the information needed to access information and send between the cloud server. This is a basic RMS voltage calculation, which then gets printed and over here gets sent to the cloud server. On the Adafruit.io cloud server, from this created solar battery performance monitoring dashboard, any measurement from the Raspberry Pi is sent to this value, which can be calculated and graphed on a running time average.
Going over the demonstration and explanation of the user interface subsystem. So to start, here is the relatively simple block diagram for the user interface. So the information gets sent from the communication apparatus to Adafruit, which is currently the database that we're looking at working with, and then it sends the information to the user interface. And that's pretty much it. So far, I'm just going to be showing on the Xcode simulator. This is simulating an iPhone 12 Pro running the application that I've made so far. It's just easier to record on the simulator. It shows the exact same thing you would see on an actual device. but again, it just makes it easier to record when everything's just on one screen. So you get in, and right now it doesn't have an app icon, but that'll be added later. And then you open it up, and it brings you to the home screen, which is My Energy. And you see you have 3 different options. You have your battery status option, you have your energy production option, and you have your energy used / cost option. And all you do is you click the button, and it brings you to the next page. And that's pretty much it. All 3 of these do the same thing, and then on each of these is where the information from the communication apparatus is going to appear. So here, it would pull in the information from Adafruit, and it will update this page accordingly. I just have to design it still and kind of get exactly how I want it to be. But other than that, that is the current state of the application or the user interface subsystem. Again, all that has to be done now is to complete the design of each of these subviews and then get the information from the database to be used in those subviews. So I plan to hopefully have the designs done in the next week and kind of go from there. Thanks.